Today we will set up our local blockchain environment for development, debugging, and deployment. We will use the Truffle framework. It's available as an npm package, so let's install it. Install Truffle, initialize empty project. We are using the unbox function to initialize a boilerplate project that we will set up an example Metacoin smart contract for us in a good overall project structure. Contracts, directory for your Solidity smart contracts. Migrations, directory for deployment files, similar but not exactly the same to Django's. Migrations folder. These migrations are used for keeping track of the changes to your smart contracts. Test, directory with test for testing your smart contracts. Truffle.js, configuration file for our local blockchain network. Inside the contracts folder are 3 smart contracts. Let's look at these. Reading good code is also an effective way to learn. This smart contract is defined with library instead of contract. This makes it a library smart contract that can be easily imported into other smart contracts. Library smart contracts are useful for containing functions you want to use in multiple other contracts, just like normal programming libraries. It also makes economic sense to keep reusable functions in one place instead of repeating them in multiple smart contracts. When deploying to the main Ethereum blockchain, we are charged by the letter, so the longer a smart contract is, the more expensive it is to deploy. We'll cover the whole deployment pipeline later. Let's move on to metacoin.sol. Immediately we notice the import of our library convertlib.sol, which indicates we'll be using the convert function somewhere down the line. Then for the first time, we see the mapping data structure. Mapping is the analog of a hash in Java and C#, or a dictionary in Python. We saw the address type yesterday in the greeting example. It represents a personal address or smart contract address. This mapping maps addresses to numbers. More specifically, it keeps a record of the balances of Metacoin coins each user has. Next, we notice an event called transfer. Events are used for generating notifications across the blockchain network to notify anyone that's listening of events happening in this smart contract. They accept arguments, which are later part of the generated notification. This is extremely useful because events take away the burden of having to process the whole blockchain when an application is interested in only a few events. For example, this event creates a notification that represents a transfer of metacoins. It contains the address of both sender and receiver, along with the value that was transferred. By listening to this event only, an application can keep track of all metacoin transactions that occur without having to process the whole Ethereum blockchain, where millions of transactions are created every day. Lastly, we have the constructor, where we set the balance of 10,000 metacoin to the address of tx.origin. Just like message was, tx is a special global variable that represents the current transaction. Any action that alters the data on the blockchain, like deploying a smart contract or executing a function that changes data, is a transaction. tx.origin represents the origin or creator of the transaction. It's similar to message.sender, but not quite the same. tx.origin can never be a smart contract address, while message.sender can. In this call chain, A, B, C, D, inside smart contract D, message sender will be C, but tx.origin will be A. However, Vitalik recommends avoiding tx.origin. The address of the default account or the Coinbase is the address that we get when we run tx.origin or message.sender in our smart contracts. Next up is the transfer from function. This one will be used by spenders to spend coins from their allowances. The send coin function is used for transferring coins from one address to another. It returns a Boolean value which indicates the success of the transfer. In the parameters, we only see the receiver's address and the amount. Only the sender can call the method. In short, only you can spend your coins. If the sender's balance is less than the amount to be sent, then we return false. Otherwise, the sender's balance is decreased by the sending amount, and the receiver's balance is increased by the same amount. Then we create a transfer event to notify anyone who is interested in these events. For example, wallet applications need to listen for events with your address so they can notify you of any funds you receive. In the end, we return true for successful transfers. The getBalance method simply checks the balances, mapping for the balance of the given address. The getBalance and ETH method also gets the balance but then converts it into Ether. In this case, the number 2 is used as a conversion rate. The Truffle command for compiling is truffle compile. On the first run, it compiles all smart contracts in the contracts directory. On any subsequent runs, it will only compile the ones that have changed. The compiled smart contracts are placed inside the new build directory in the subfolder contracts. There is one JSON file for each smart contract. We will come back to these files later. Next, we need to set up our truffle.js file with our local network IP, port, and network ID. We'll use the default configuration from their documentation. Now, let's finally deploy these smart contracts to our local blockchain. Open a second terminal and run truffle develop. This will bring up a new local blockchain out of the blue. By default, the local blockchain runs on localhost 9545. Make sure this matches the port in your truffle.js file. Now, back in the first terminal, run Truffle Migrate. In the output of the migrate command, you'll get this. Notice these lines: migrations, convert lib, metacoin. These are the addresses where each smart contract is deployed. The Ethereum blockchain makes a distinction between writing data to the blockchain and reading data from it. This distinction plays an important role in how you write your application that interacts with the blockchain. Writing data is called a transaction, while reading data is called a call. Transactions and calls are processed very differently. Transactions change the state of the blockchain. A transaction can be as simple as sending Ether to another account, or as complicated as executing a contract function or deploying a new contract to the blockchain. The main characteristic of a transaction is that it writes, or changes, data. That is why transactions cost Ether, known as gas, to run, and they take time to process. When you execute contracts function, you create a transaction. You cannot receive that function's return value because the transaction isn't processed immediately. These functions will return a transaction ID instead. We can use this transaction ID later on to check the status of the transaction on the blockchain and see if it is executed yet or not. This is why events are so useful. They allow your application to listen passively for events to happen, instead of actively checking the transaction status on the blockchain. In summary, the most important properties of transactions are: they change the state of the blockchain, therefore they cost gas. They are not processed immediately. They return transaction ID and receipt. Calls are almost the exact opposite of transactions. They can be used to execute code on the blockchain, but no data will be permanently changed. They are free to run, and their defining characteristic is they read data. If we execute a contract function that is a call, we receive the return value straight away, or synchronously. In summary, important properties of calls are: they don't change the state of the blockchain, so they are free to execute. They are processed immediately, and they return a value. In short, the difference between a transaction and a call becomes a choice to either read or write data. After the migration is complete, we now have available JavaScript objects for every smart contract we deployed. Write the following code in the second terminal where we ran truffle develop. This will print out the full deployed instance of the metacoin contract. Let's make our first interaction by checking the balance of the owner's address. You can see the default owner, called Coinbase, by typing in the Truffle console. To see all accounts in the local blockchain, run. The address of the default account, or the Coinbase, is the address that we get when we run tx.origin or message.sender in our smart contracts. This means that all 10,000 Metacoin tokens should be in the balance of this Coinbase account. Let's check its balance. That prints out 10,000. We call the getBalance function as getBalance.call. This represents a call, not a transaction. That is why we got the result straight away. Let's make our first blockchain transaction by making a transfer. we will use the sendCoin function to transfer 9 coins from the Coinbase account to some of the other accounts on the blockchain. We passed 3 arguments to the sendCoin function, even though it expects only 2 in the definition. The last argument, passAsObject, allows us to alter special properties of the transaction itself. In this case, we set the origin of the transaction to be the Coinbase account, since that is where all the coins are. As a result, we see the full transaction object. If you look closely, you'll notice the status value in the transaction response. Status 1 means the transaction is processed, while 0 means it is unprocessed. Let's check the balance of the target and Coinbase accounts. The source has 9,991 left, while the target account has 9. Today, we covered a lot. First, we installed Truffle and set up our local blockchain network. Then we looked at 2 more smart contracts. The first one was a library, and the second one was a pseudo coin. We learned the key differences between a call and a transaction. In the end, we made some interactions with a smart contract simulating the actions an application would perform.